An ignition system is a system for igniting a fuel-air mixture. Ignition systems are well known in the field of internal combustion engines such as those used in petrol engines used to power the majority of motor vehicles, but they are also used in many other applications such as in oil-fired and gas-fired boilers, rocket engines, etc. The first ignition system to use an electric spark was probably Alessandro Volta's toy electric pistol from the 1780s. Virtually all petrol engines today use an electric spark for ignition. Diesel engines rely on fuel compression for ignition, but usually also have glow plugs that preheat the combustion chamber to allow starting of the engine in cold weather. Other engines may use a flame, or a heated tube, for ignition. History. Magneto systems. The simplest form of spark ignition is that using a magneto. The engine spins a magnet inside a coil, or, in the earlier designs, a coil inside a fixed magnet, and also operates a contact breaker, interrupting the current and causing the voltage to be increased sufficiently to jump a small gap. The spark plugs are connected directly from the magneto output. Early magnetos had one coil, with a contact breaker inside the combustion chamber. In about 1902, Bosch introduced a double-coil magneto, with a fixed sparking plug, and the contact breaker outside the cylinder. Magnetos are not used in modern cars, but because they generate their own electricity they are often found on piston-engined aircraft engines and small engines such as those found in mopeds, lawnmowers, snowblowers, chainsaws, etc. Where a battery-based electrical system is not present for any combination of necessity, weight, cost, and reliability reasons. Magnetos were used on the small engine's ancestor, the stationary hit-and-miss engine which was used in the early 20th century, on older gasoline or distillate farm tractors before battery starting and lighting became common, and on aircraft piston engines. Magnetos were used in these engines because their simplicity and self-contained operation was more reliable, and because magnetos weighed less than having a battery and dynamo or alternator. Aircraft engines usually have dual magnetos to provide redundancy in the event of a failure, and to increase efficiency by thoroughly and quickly burning the fuel-air mix from both sides towards the center. The Wright brothers used a magneto invented in 1902 and built for them in 1903 by Dayton, Ohio inventor, Vincent Grabbe-Apple. Some older automobiles had both a magneto system and a battery-actuated system running simultaneously to ensure proper ignition under all conditions with the limited performance each system provided at the time. This gave the benefits of easy starting with reliable sparking at speed. Switchable systems. The output of a magneto depends on the speed of the engine, and therefore starting can be problematic. Some magnetos include an impulse system, which spins the magnet quickly at the proper moment, making easier starting at slow cranking speeds. Some engines, such as aircraft but also the Ford Model T, used a system which relied on non-rechargeable dry cells, to start the engine or for starting and running at low speed. The operator would manually switch the ignition over to magneto operation for high-speed operation. To provide high voltage for the spark from the low-voltage batteries, a tickler was used, which was essentially a larger version of the once widespread electric buzzer. With this apparatus, the direct current passes through an electromagnetic coil which pulls open a pair of contact points, interrupting the current. The magnetic field collapses, the spring-loaded points close again, the circuit is re-established, and the cycle repeats rapidly. The rapidly collapsing magnetic field, however, induces a high voltage across the coil which can only relieve itself by arcing across the contact points. While in the case of the buzzer this is a problem as it causes the points to oxidize and/or weld together, in the case of the ignition system this becomes the source of a high voltage to operate the spark plugs. In this mode of operation, the coil would buzz continuously, producing a constant train of sparks. The entire apparatus was known as the Model T spark coil. Long after the demise of the Model T as transportation they remained a popular self-contained source of high voltage for electrical home experimenters, appearing in articles in magazines such as Popular Mechanics and projects for school science fairs as late as the early 1960s. In the UK, these devices were commonly known as trembler coils and were popular in cars pre-1910, and also in commercial vehicles with large engines until around 1925 to ease starting. The Model T differed from modern implementations by not providing high voltage directly at the output. The maximum voltage produced was about 30 volts, and therefore also had to be run through the spark coil to provide high enough voltage for ignition, as described above, although the coil would not buzz continuously in this case, only going through one cycle per spark. In either case, the low voltage was switched to the appropriate spark plug by the timer mounted on the front of the engine. This performed the equivalent function to the modern distributor, although by directing the low voltage, not the high voltage as for the distributor. The timing of the spark was adjustable by rotating this mechanism through a lever mounted on the steering column. As the precise timing of the spark depends on both the timer and the trembler contacts within the coil, this is less consistent than the breaker points of the later distributor. However, for the low speed and the low compression of such early engines, this imprecise timing was acceptable. Battery and coil-operated ignition. With the universal adoption of electrical starting for automobiles, and the availability of a large battery to provide a constant source of electricity, magneto systems were abandoned for systems which interrupted current at battery voltage, used an ignition coil to step the voltage up to the needs of the ignition, and a distributor to route the ensuing pulse to the correct spark plug at the correct time. The first reliable battery-operated ignition was developed by the Dayton Engineering Laboratories Company and introduced in the 1910 Cadillac. This ignition was developed by Charles Kettering and was a wonder in its day. It consisted of a single coil, points, a capacitor and a distributor set up to allocate the spark from the ignition coil timed to the correct cylinder. The coil was basically a transformer to step up the low battery voltage to the high ignition voltage required to jump a spark plug gap. The points allow the coil magnetic field to build, and then, when the points are opened by a cam arrangement, the magnetic field collapses and a large voltage is produced. The capacitor has two functions: 1, it absorbs the back EMF from the magnetic field in the coil to minimize point contact burning and maximize point life. And 2, it forms a resonant circuit with the ignition coil transferring further energy to the secondary side until the energy is exhausted. The Kettering system became the primary ignition system for many years in the automotive industry due to its lower cost, higher reliability and relative simplicity. Modern ignition systems. The ignition system is typically controlled by a key-operated ignition switch. Mechanically timed ignition. Most four-stroke engines have used a mechanically timed electrical ignition system. The heart of the system is the distributor. The distributor contains a rotating cam driven by the engine's drive, a set of breaker points, a condenser, a rotor and a distributor cap. External to the distributor is the ignition coil, the spark plugs and wires linking the distributor to the spark plugs and ignition coil. The system is powered by a lead-acid battery, which is charged by the car's electrical system using a dynamo or alternator. The engine operates contact breaker points, which interrupt the current to an induction coil. The ignition coil consists of two transformer windings sharing a common magnetic carrier, the primary and secondary windings. An alternating current in the primary induces alternating magnetic field in the coil's core. Because the ignition coil's secondary has far more windings than the primary, the coil is a step-up transformer which induces a much higher voltage across the secondary windings. For an ignition coil, one end of windings of both the primary and secondary are connected together. This common point is connected to the battery. The other end of the primary is connected to the points within the contact breaker. The other end of the secondary is connected, via the distributor cap and rotor, to the spark plugs. The ignition firing sequence begins with the points closed. A steady charge flows from the battery, through the current-limiting resistor, through the coil primary, across the closed breaker points and finally back to the battery. This steady current produces a magnetic field within the coil's core. This magnetic field forms the energy reservoir that will be used to drive the ignition spark. As the engine turns, so does the cam inside the distributor. the points ride on the cam so that as the engine turns and reaches the top of the engine's compression cycle, a high point in the cam causes the breaker points to open. This breaks the primary windings circuit and abruptly stops the current through the breaker points. Without the steady current through the points, the magnetic field generated in the coil immediately and rapidly collapses. This change in the magnetic field induces a high voltage in the coil's secondary windings. At the same time, current exits the coil's primary winding and begins to charge up the capacitor that lies across the now open breaker points. This capacitor and the coil are unregistered trademark S primary windings form an oscillating LC circuit. This LC circuit produces a damped, oscillating current which bounces energy between the capacitor unregistered trademark S electric field and the ignition coil unregistered trademark S magnetic field. The oscillating current in the coil unregistered trademark S primary, which produces an oscillating magnetic field in the coil, extends the high voltage pulse at the output of the secondary windings. This high voltage thus continues beyond the time of the initial field collapse pulse. The oscillation continues until the circuit unregistered trademark S energy is consumed. The ignition coil's secondary windings are connected to the distributor cap. A turning rotor, located on top of the breaker cam within the distributor cap, sequentially connects the coil's secondary windings to one of the several wires leading to each cylinder's spark plug. The extremely high voltage from the coil's secondary causes a spark to form across the gap of the spark plug. This, in turn, ignites the compressed air-fuel mixture within the engine. It is the creation of this spark which consumes the energy that was stored in the ignition coil unregistered trademark S magnetic field. The flat twin-cylinder 1948 Citroën N2CV used one double-ended coil without a distributor, and just contact breakers, in a wasted spark system. Some two-cylinder motorcycles and motor scooters had two contact points feeding twin coils each connected directly to the spark plug without a distributor. For example, the BSA Thunderbolt and Triumph Tigress. High-performance engines with 8 or more cylinders that operate at higher PM demand both a higher rate of spark and a higher spark energy than this simple ignition circuit can provide. This problem is overcome by using either of these adaptations. Two complete sets of coils, breakers and condensers can be provided, one set for each half of the engine, which is typically arranged in V8 or V12 configuration. Although the two ignition system halves are electrically independent, they typically share a single distributor which in this case contains two breakers driven by the rotating cam, and a rotor with two isolated conducting planes for the two high-voltage inputs. A single breaker driven by a cam and a return spring is limited in spark rate by the onset of contact bounce or float at higher PM. This limit can be overcome by substituting for the breaker a pair of breakers that are connected electrically in series but spaced on opposite sides of the cam so they are driven out of phase. Each breaker then switches at half the rate of a single breaker and the dwell time for current buildup in the coil is maximized since it is shared between the breakers. The Lamborghini V12 engine has both these adaptations and therefore uses two ignition coils and a single distributor that contains 4 contact breakers. A distributor-based system is not greatly different from a magneto system except that more separate elements are involved. There are also advantages to this arrangement. For example, the position of the contact breaker points relative to the engine angle can be changed a small amount dynamically, allowing the ignition timing to be automatically advanced with increasing revolutions per minute or increased manifold vacuum, giving better efficiency and performance. However, it is necessary to check periodically the maximum opening gap of the breaker, S, using a feeler gauge, since this mechanical adjustment affects the dwell time during which the coil charges, and breakers should be redressed or replaced when they have become pitted by electric arcing. This system was used almost universally until the late 1970s, when electronic ignition systems started to appear. Electronic ignition. The disadvantage of the mechanical system is the use of breaker points to interrupt the low-voltage high current through the primary winding of the coil. The points are subject to mechanical wear where they ride the cam to open and shut, as well as oxidation and burning of the contact surfaces from the constant sparking. They require regular adjustment to compensate for wear, and the opening of the contact breakers, which is responsible for spark timing, is subject to mechanical variations. In addition, the spark voltage is also dependent on contact effectiveness, and poor sparking can lead to lower engine efficiency. A mechanical contact breaker system cannot control an average ignition current of more than about 3 A while still giving a reasonable service life, and this may limit the power of the spark and ultimate engine speed. Electronic ignition solves these problems. In the initial systems, points were still used, but they handled only a low current which was used to control the high primary current through a solid-state switching system. Soon, however, even these contact breaker points were replaced by an angular sensor of some kind, either optical, where a vaned rotor breaks a light beam, or more commonly using a Hall effect sensor, which responds to a rotating magnet mounted on the distributor shaft. The sensor output is shaped and processed by suitable circuitry, then used to trigger a switching device such as a thyristor, which switches a large current through the coil. The first electronic ignition was tested in 1948 by Delco Remy, while Lucas introduced a transistorized ignition in 1955, which was used on BRM and Coventry Climax Formula One engines in 1962. The aftermarket began offering EI that year, with both the Autolite electric transistor 201 and Tungsol EI4 being available. Pontiac became the first automaker to offer an optional EI, the brakeless magnetic pulse trigger Delcatronic, on some 1963 models. It was also available on some Corvettes. The first commercially available all-solid-state capacitive discharge ignition was manufactured by Hilland Electronics in Canada also in 1963. Ford fitted a Lucas system on the Lotus 25s entered at Indianapolis the next year, ran a fleet test in 1964, and began offering optional EI on some models in 1965. Beginning in 1958, Earl W. Mayer at Chrysler worked on EI, continuing until 1961 and resulting in use of EI on the company's NASCAR HEMIS in 1963 and 1964. Pristolite CD65, which relied on capacitance discharge, appeared in 1965, and had an unprecedented 50,000-mile warranty. A similar CD unit was available from Delco in 1966, which was optional on Oldsmobile, Pontiac, and GMC vehicles in the 1967 model year. Also in 1967, Motorola debuted their brakeless CD system. The most famous aftermarket electronic ignition, which debuted in 1965, was the Delta Mark X capacitive discharge ignition, which was sold assembled or as a kit. Fiat became the first company to offer standard EI, in 1968, followed by Chrysler in 1973 and by Ford and GM in 1975. In 1967, Pristolite made a black box ignition amplifier, intended to take the load off of the distributor's breaker points during high RPM runs, which was used by Dodge and Plymouth on their factory Superstock Coronet and Belvedere drag racers. This amplifier was installed on the interior side of the car's firewall, and had a duct which provided outside air to cool the unit. The rest of the system remains as for the mechanical system. The lack of moving parts compared with the mechanical system leads to greater reliability and longer service intervals. Chrysler introduced brakeless ignition in mid-1971 as an option for its 340 V8 and the 426 Street Hemi. For the 1972 model year, the system became standard on its high-performance engines and the 4-barrel carburetor-equipped 400 HP 400 Acleon, and was an option on its 318 Acleon, 360 Acleon, 2-barrel 400 Acleon, and low-performance 440 Acleon. Brakeless ignition was standardized across the model range for 1973. For older cars, it is usually possible to retrofit an EI system in place of the mechanical one. In some cases, a modern distributor will fit into the older engine with no other modifications, like the HEI distributor made by General Motors, the Hot Spark electronic ignition conversion kit and the aforementioned Chrysler-built electronic ignition system. Other innovations are currently available on various cars. In some models, rather than one central coil, there are individual coils on each spark plug, sometimes known as direct ignition or coil-on plug. This allows the coil a longer time to accumulate a charge between sparks, and therefore a higher energy spark. A variation on this has each coil handle 2 plugs, on cylinders which are 360 degrees out of phase. In the 4-cycle engine this means that one plug will be sparking during the end of the exhaust stroke while the other fires at the usual time, a so-called wasted spark arrangement which has no drawbacks apart from faster spark plug erosion. The paired cylinders are 1/4 and 2/3. Other systems do away with the distributor as a timing apparatus and use a magnetic crank angle sensor mounted on the crankshaft to trigger the ignition at the proper time. Digital electronic ignitions. At the turn of the 21st century, digital electronic ignition modules became available for small engines on such applications as chainsaws, string trimmers, leaf blowers, and lawnmowers. This was made possible by low-cost, high-speed, and small-footprint microcontrollers. Digital electronic ignition modules can be designed as either capacitor discharge ignition or inductive discharge ignition systems. Capacitive discharge digital ignitions store charged energy for the spark in a capacitor within the module that can be released to the spark plug at virtually any time throughout the engine cycle via a control signal from the microprocessor. This allows for greater timing flexibility, and engine performance, especially when designed hand-in-hand with the engine carburetor. Engine management. In an engine management system, electronics control fuel delivery and ignition timing. Primary sensors on the system are crankshaft angle position, airflow into the engine and throttle position. The circuitry determines which cylinder needs fuel and how much, opens the requisite injector to deliver it, then causes a spark at the right moment to burn it. Early EM systems used an analog computer to accomplish this, but as embedded systems dropped in price and became fast enough to keep up with the changing inputs at high revolutions, digital systems started to appear. Some designs using an EMS retain the original ignition coil, distributor and high-tension leads found on cars throughout history. Other systems dispense with the distributor altogether and have individual coils mounted directly atop each spark plug. This removes the need for both distributor and high-tension leads, which reduces maintenance and increases long-term reliability. Modern EMSs read in data from various sensors about the crankshaft position, intake manifold temperature, intake manifold pressure, throttle position, fuel mixture via the oxygen sensor, detonation via a NOx sensor, and exhaust gas temperature sensors. The EMS then uses the collected data to precisely determine how much fuel to deliver and when and how far to advance the ignition timing. With electronic ignition systems, individual cylinders can have their own individual timing so that timing can be as aggressive as possible per cylinder without fuel detonation. As a result, sophisticated electronic ignition systems can be both more fuel efficient, and produce better performance over their counterparts. Turbine, jet and rocket engines. Gas turbine engines, including jet engines, have a CDI system using one or more igniter plugs, which are only used at startup or in case the combustor flame goes out. Rocket engine ignition systems are especially critical. If prompt ignition does not occur, the combustion chamber can fill with excess fuel and oxidizer and significant overpressure can occur or even an explosion. Rockets often employ pyrotechnic devices that place flames across the face of the injector plate, or, alternatively, hypergolic propellants that ignite spontaneously on contact with each other. The latter types of engines do away with ignition systems entirely and cannot experience hard starts, but the propellants are highly toxic and corrosive. See also, Saab direct ignition, spark ignition, Charles Kettering, the inventor of the battery ignition system. Electromagnetism, Faraday's law of induction, ignition coil, inductor, induction coil, magnetic field, transformer. References